Okay, we're ready to start. Today, we will study the theory of time calculus, or more precisely, we will study exact mathematical formulas that can be used to map different viewpoints, and we will see interesting applications to simulations, to understanding in particular what we can call perfect simulations, simulations without transients. The only difficulty this is a chapter that is not very much known because probably there is a conceptual difficulty in understanding the framework. So we'll first go through the framework. We assume that time calculus applies to stationary processes. When we have done simulation, we have seen that a simulation is typically not always stationary. Even if it is stationary, it is typically not so at the beginning, so we need to remove a warm-up phase. So this applies to something like a simulation after removing the warm-up phase. So I assume I have a simulation that has a stationary regime and from which I've eliminated the initial transients, and I call S of t the state of the simulation. It's the state of everything. So my simulation uses a number of variables. So it's the state of all the variables, usually something very complex that we cannot enumerate because it has exponential complexity, but intellectually it's convenient to use it in that way. Then we assume that we measure something at time t that I call xt. For example, st is the complete state of a queuing system, and xt is the size of the queue in number of jobs at time t. And a key assumption is that we will apply time calculus to things like xt, but in order for time calculus to be applicable, we need this red assumption here. We need that the thing Sx is stationary, so the global thing, so jointly stationary. What does it mean? It means that the classical definition of stationary that we have here, we will see that in practice, it means that St is a stationary distribution, and the thing we are observing depends on the simulation state in a way that's invariant by shift of time origin. Right? So, for example, we've done simulations of the random waypoint mobility model. Then we can call St the current position of the mobile, and everything we need to have the complete simulation state. So the position of the mobile itself is not sufficient. When I say everything we need for the simulation state, it means assume you stop your computer, the operating system stops your simulation and interrupts it to serve another job of the computer. Then in order to restart the simulation correctly somewhere, you need to have some state, which is what the operating system does. It's the state of all the variables that you've used. So that's St here. So for the random waypoint, we need the current position, plus a few other things. We need, in particular, the position of the next waypoint. We're moving to our next point, so to continue the simulation, we need to know where we go. Also, at which speed we're going. And that's all we need, because at the next waypoint, we will draw things randomly independent of the past. So we don't need to draw them in advance. We can draw them just when we reach the waypoint. So for the random waypoint, St is this. Things that are jointly stationary with xt is, for example, the current speed at time t, or the time to be run until the next waypoint, how much time is left in the current trip until we reach the next waypoint. We can ask the question about this. And all of this satisfy this assumption here. They are invariant by a shift of time origin. If I decide that time 0 is now or 20 minutes ago, those things, the value of x will not change. Things that would violate this assumption is, for example, the absolute time at which the last waypoint occurred. I'm asking a mobile now, at which time did you start your trip? So this question, of course, is not satisfying this assumption. So that's the first thing we need to watch. This is not very difficult, but it's a small caveat. Then the most interesting thing is to give sense to what we call the arbitrary point in time. We have discussed already that if I take a point in a rectangle, I can say what is an arbitrary point in a rectangle, what is usually meant by this. Yes, it's a point drawn uniformly at random, but for time we can't do that. So it's by necessity a bit more complicated. We will say that so the trick is to say, since the simulation is stationary, xt, st, the vector xs is stationary, then the expectation of xt, or the distribution of xt, or the expectation of any function of xt, does not depend on time, t, because that's a consequence or definition of stationarity. So the arbitrary point in time, in fact, in this setting, amounts to saying it doesn't matter at which time you look at the system if the system is in stationary regime. So you let it go into stationary regime, then you stop it, you freeze it, you observe the things, and that is what mathematicians call the arbitrary point in time. It can be shown, there are proofs for simple cases in the lecture note, that what we discussed already, it's the same viewpoint as that seen by an external observer who observes the system at a random time obtained from the Poisson process, who is independent of the simulation. So the observer should not decide whether to sample the system now based on what happens in the simulation. The observer should decide by looking at its clock, oh, it's time for me to go. My Poisson clock has fired, I will go and observe the system. So if you do it in that way, you obtain a distribution which is perhaps easier to understand and to accept than the stationary thing here. And the two have the same distribution. Now to do PAM calculus, we need to define what is a stationary point process. So what is a point process? A point process in time, we could call it a stationary time process, is simply a collection of time instants, Tn, increasing, that are related typically to the simulation by the fact that there are times at which something happens for the simulation. Something means, remember the simulation as a state, st. The state belongs to a state script s, curly s here. Then I can define a subset of the Cartesian product of S by itself, which I can interpret as transitions. When the state changes from some value to another, I decide that there is something, an event of interest. And the time at which it occurs, I call it a selected transition. So formally, S of t plus S of t minus, so this sign indicates that it's the state just after t and here just before. It's sometimes people assume that most stochastic process systems assume that trajectories are continuous to the right. So st plus would be st, but not always done. In some physics paper, you do the opposite. So with the take-home messages, we don't really know. So I make it clear here what it means. So just before t, I was in a given state. Just after I am in a different state, if that state belongs to that specified specific thing, I say I have an event of interest. For example, it could be, if the simulation state is the queuing system, it could be an arrival. An arrival is when the number of customers in the queue increases by 1. So the set F0 are the set of all possible states such that the first coordinate and the second differ by exactly 1. Positive thing here. So such a thing is called a stationary point process. It is stationary in the sense that the statistics of the sequence of times, if I take a sequence of times, T1, T2, T3, etc., the statistics, the joint statistics of T1, T2, T3, etc., are the same as T100, 101, 102, 103. If the simulation is stationary here. In this setting, then very often what is done in the context of network calculus, of a PAM calculus paper, is to call t equals 0 the arbitrary point in time. So we say I have a simulation that is in stationary regime. I call t equals 0 the time now. And since any time is as good as any others, I consider this as the arbitrary point in time. And then, if I take this convention, of course, there will be events that have occurred before, infinitely many, probably, for most simulations, and infinitely many in the future as well, in the past and in the future. So that if I take a typical interval between two events, it's the interval t0, t1. It's one convention that's often used. Not always, but very often, and it makes the notation a bit easier. I mean, difficulty with Palm calculus is really the notation and the framework. The Palm expectation is then defined as, remember, we're interested in some quantity x of t. For example, the number of messages or customers in the queue. Right? Then we call the Palm expectation at time t. We put a little t in exponent in the expectation symbol as the expectation of the quantity xt, given that exactly at time t there is a special event, a selected transition occurs. For example, if I'm interested in my queue, I could say, what is the expected number of customers exactly when there is an arrival here? That doesn't shock you? Well, it should, because to define a conditional probability or a conditional expectation, what's the definition of a conditional something? Expectation of x given A is the expectation of x times the indicator function of A divided by the probability of the event A occurring. Now, for most realistic models, the probability of, for example, for a Poisson process, the probability that there is an arrival exactly at time t is 0, because we're in continuous time. Right? In discrete time, it's different. If we have discrete times, then at every discrete time there is or there is not an arrival. But in continuous time, the probability of being exactly between t and t is 0. Right? We know the probability of being between t and t plus dt is the PDF multiplied by dt, but if we shrink dt to 0, we obtain 0. So this is not a formal definition. It's true in discrete time. In discrete time, it's exactly this. In continuous time, you need a bit of work to make sense of that. It's in the category of measure theory. You need to take a limit of something. We will not go through that. If you think in discrete time, then it is the classical conditional probability. If you assume there is a tick of the clock every nanosecond, and if you have a Poisson process, the probability that at this tick of the clock there is an arrival is equal to lambda times 1 nanosecond. Right? So you flip a coin every tick, and then that is really this, right? It is the expectation of x, given that you happen to be at one of the ticks of the clock here. Now, if you write this in discrete time using the formal definition of conditional things, you can see that this should be independent of time t because of the stationarity assumption. So this should be true. And this thing here is called the Palm expectation. So the Palm expectation of something is x measured at time t, is the average of something sampled at an arbitrary event time, Tn. Right? It's a bit complicated here, but we will need this complication to make sense of the formalism that will give us formulas that we can apply mechanically here. For example, if I'm looking at the random waypoint model, and I call the selected events the events that a mobile reaches the end of a trip. Right? So you reach, remember, with a random waypoint model, you go to a certain point. When you reach that point, we say there is a selected event. That's an instant of interest here. Right? Now, I can call the xt the speed that I have at time t. Then what would be the expectation of x0 is the expected speed, the average speed observed at an arbitrary waypoint. Which is, if we follow, for example, the one we did in the lab, it's drawn from the distribution that is given. For example, uniform between Vmin and Vmax. Right? So, first that's a very important thing. The take-home thing to remember, the Palm expectation of something is the average of that something sampled at an arbitrary event, which is the interpretation we gave last week. We looked at the size of something sampled according to some specific method. Here we sample at an arbitrary time of trip end, right? So an arbitrary index n here. So here is our random waypoint here. So remember, you go from one to the next. And we see there is a difference between expectation of x0, which is the Palm expectation of the speed, which is the speed observed at trip n, versus the time stationary speed observed at an arbitrary point in time. Why are they different?
Smaller speeds take up longer time.
Because a smaller speed takes up longer time. So if I decide to have a small speed on this segment here, I will stay for a long period on this segment. So if I ask at an arbitrary point in time, what's your speed? I'm more likely to find small speeds than large speeds. This is what we have seen in the lab. This is what I mentioned about the formal definition. Formal distribution of the conditional distribution is given by this here. In continuous time, as I mentioned, it's a bit more complicated. We'll not go through it. I talked of expectation. Expectation or probabilities are the same. If I can give the expectation of any function that I observe, is the same as giving a distribution. So the Palm probability is the same. Palm probability of an event is the probability of this event, given that at exactly this time there was a selected transition. We can easily make the link with the interpretation we did last week, which was based on simulations. It's called the ergodic interpretation. If the simulation is stationary and ergodic, ergodic means that sample paths averages converge to expectations. Right? That's a very important property, and that causes also a lot of confusion, and that justifies why confusion is often done. When I talk of the expected speed at an arbitrary point in time, for example, intellectually, in theory, what does the expectation mean? Well, it means, assume you redo the experiment 1 zillion times, 1 zillionth independent replication of the simulation. You ask at each replication, what's the value? And you take the average over these zillion independent replications. That's the central limit theorem. That's the law of large numbers that says that if you do independence many times, something drawn independently from the given distribution, that converges to the expectation. And if you do that for any arbitrary test function, you obtain the distribution here. Very often, that's not what we do. What we do is we have a single long simulation or a single long data set, and we take the average over the data set. And we say that's the expectation. It's an expectation, but it's a different one. There's a difference between the two. The first one is saying, I imagine this data set has been produced from a simulator, and I have only one run of the simulator. But in my head, there are zillions of possible runs that could have been possible. The second interpretation is that I look at my single run and I do the average over the entire run here. A priori, those two things are different. And in general, they may be different, but there are lots of systems that are stationary for which those two averages are the same. In particular, such systems are called ergodic. So if ergodic means essentially that the sample path averages converge to expectation. Right? An example of system that's ergodic is a queuing system. a single queue. If you simulate a single queue that is stable, rho less than 1, then sooner or later the queue will empty. If rho is equal to 0.999, it may take you an astronomically long time to observe that, but it will happen sooner or later. So in the intellectual world of models, it will happen with probability 1. Then once it has happened, you have a reset point where it's like your initial condition was empty. And from that point, again, with probability 1, it will become empty again. So the system, if you wait long enough, will repeat itself, will go through regeneration point, so that if you wait long enough to see a large number of regeneration points, then you're going to see all the possible states of the simulations, and therefore you will get something close to the expectation. That's the essence of ergodic systems. Ergodic systems are typically systems that are stable, that have a stationary regime, and that have a unique stationary regime. For Markov chains, in fact, on finite states, it's exactly the same thing here. There are systems that don't have a unique stationary regime. Those are, for example, systems that can fail and have different failure modes. So the stationary regime is failed, but you may fail in different way. Right? You may die of cholera or of a road accident, then your final state is not the same. So such systems are not ergodic. Right? So ergodic systems don't exist in nature, they exist in mathematics, but they are quite useful. And when we interpret things with simulations, we implicitly assume that we're testing a system that is ergodic. Then, in this interpretation, we have that the expectation of x0, remember with this notation, x0 is the arbitrary point in time, so that's the time stationary average, and it's, in my simulation, the limits that I would have of the averages at every point in time. Here I'm assuming discrete time, so I discretize time, and I take the average over a long period of time here. The Palm expectation of x0, here 0 means also time 0, but here it means a time that is specifically a transition of interest, a selected transition of interest. Then this would be equal, with probability 1, to the limit when n becomes very large of the average over the number of transitions here. Voila, so that's the framework. That's a bit painful, but now that we've gone through it, we can do interesting things. The first thing is to have what we call the intensity formula. What is the intensity? Well, for any framework like we have, i.e. a stationary point process with selected a state of transition st and selected time instance tn, then the number of events per time unit is well defined. The expected number of events per time unit is well defined, and it's called the intensity of the system of transitions here. For example, in a simulation, if I have capital N events in a simulation that lasts t sub n, in order to see capital N events, then lambda would be n divided by Tn. That would be my estimate of Tn. That's why it's called an intensity. Over the time axis, I have seen n points over an interval t, then intensity is the density in time is n divided by Tn. So it's the inverse of a time here. For a Poisson process, the intensity is exactly the lambda of the Poisson process. So a Poisson process is such that the time between events is exponential with parameter lambda. And for this, it can be shown that the intensity is exactly lambda. In fact, we will see it in a minute, how we can get this for the Poisson process. For other processes, like the random waypoint simulation that we did, the intensity might be more difficult to compute. We can compute it by simulation, by doing this, right here. But it might require a bit more work to compute, but certainly the way it's defined is easy to understand. It's defined as the average number of waypoints that are reached per time unit. So if I do a simulation, how many trips do I do per time unit? Per hour, for example. But there is a very simple way to define and compute the intensity. which is our first Palm calculus formula, which is called the intensity formula. It's given here. 1 over the intensity is the Palm expectation of T1 minus T0 is equal to the Palm expectation of T1. Right? So first, let's simplify a bit. What does that mean here? Well, remember that in this setting, we assume that time 0 is the arbitrary point in time, and T0 is by definition the transition that was just before time 0, and T1 is the next one here. So this is the assumption we make here. So, and the Palm expectation of T1 minus T0 means the length of this interval. Palm means assuming that at time 0 there is an event. So that means assuming T0 is equal to 0. Right? So that's why this is equal to that. So this is just notation. There is nothing, there is no information in those things. The information is here. This is 1 over lambda. So in more mundane terms, it is simply saying that the intensity is 1 over the mean time between events. Right? Which seems obvious if we do things the way we did last week, because in a simulation, in a long simulation, the lambda will be n over Tn, and the average time interval duration will be Tn over n. Right? I've observed, I've observed the sum of all the intervals will be, if we ignore the rounding due to the breaking of the first of the last interval, will be the length of the simulation divided by n. But it is formally true for any process that is stationary as we have defined. The two are exactly equal. So first formula, the expected number of events of a stationary process per time unit is 1 over the average duration of the time between two consecutive events. Which is useful, not surprising, but we never know for that kind of things because 1 over is a nonlinear transformation. So is it true? Yes, here it is true. So if we go back to the Poisson process, we know that the mean time between events is the expectation of the exponential distribution, 1 over lambda. So the intensity is lambda. We know that from other means. We know, if you look up in Wikipedia or textbooks, you will find the number of transitions of a Poisson process between an interval of duration t is a Poisson random variable with expectation lambda t. It will give us the same thing here. For the random waypoint model, then it tells us the intensity is what? Well, it's the average time between two visits to endpoints, which is the average trip duration. How much time does it take to run on a segment given the rules of the random waypoint, which we will compute a bit later. Voilà, I've done a long introduction. It's time for you to be active a bit. So here is a first question. Buses at the bus stop are arriving at an interval that's uniformly distributed between 15 and 25 minutes. Right? What can we say? And the correct answer is B, at least if we accept the formalism we've seen a minute ago. The average time between events is the expectation of this uniform thing, which is 20 minutes. So in hours, it's 1 over 3. So the intensity is 1 over 1 over 3, which is 3. So if this system would be stationary, if it would stay forever, which probably is not true, it stops at night probably. But if we assume it would stay forever, we could say there are 3 buses in average per hour, which is one way to say the intensity is 3. Or at least if we assume enough things, so what do we need to assume for this to be true? And the answer is B. We could say that's a strong assumption, but I think the remarkable thing is that we don't need A, we don't need C. Right? Very often, in order to do tractable modeling, we assume Poisson things or we assume independent arrivals here. Here, there's nothing of that kind. And the way to remember why is to do what we did last week. In order to evaluate those relationship between different quantities. We did long simulations and we compared one average and the other. When we do that, we're not assuming any kind of independence of or given distribution. We're just averaging things. That was our first formula. In fact, our first formula is an instance of the second one, which is there are multiple pulp calculus formula. You can find many of them in the lecture note, but we'll use essentially only this one because this will give us a long way, which is called the inversion formula. So that relates expectation of xt equal expectation of x0. Remember, we assume we observe some quantity x at time t of the stationary. So everything is stationary. So the expectation of xt is the same as expectation of x0. Remember, other than stationary, x is anything. So this formula contains the full distribution of x because I can replace x by any test function of x. Right? So on the left, we have the time stationary viewpoint. That's what we obtain if we sample the system at an arbitrary point in time. Then it is equal to this formula. This formula is the intensity multiplied by the Palm expectation of something. Now the something is itself an integral. So this something is the integral from 0 to t1. Now since we do Palm expectation, remember that we condition on the fact that at time 0 there is an event. So this is saying this is the integral over a time interval between this transition that occurs now and the next. We take the integral of x here. So what we do here is the integral of the value of x. So if we divide by t1 minus t0, we would have the time average value of x between two transitions. So this is saying you take this, you look in average by averaging at an arbitrary transition, and then since we did not divide by 1 over t, you multiply by lambda, which in some sense takes care of this renormalizing here. And this is exact. If you do this, you have exactly the same two things. So the expectation of x averaged at an arbitrary point in time is the same as taking the time average between two typical transitions and rescaling by lambda. Let's see a classical example, which is used in queuing systems for the waiting time. So let's go back to our bus systems. Here, I assume I have a stationary bus arrival process. So that's a model of the busy hour, for example, or the off-peak hour. Of course, this is valid only as a stretch of imagination for some limited period of time. I call Tn the arrival of buses that are marked by bars on this time axis here. I arrive at an arbitrary point in time t because I'm not synchronized with the bus, and I ask what's the waiting time for me. So x of t is the waiting time for somebody who arrives at time t. Then it's easy to verify that x of t is a valid thing to apply Palm calculus because if it's independent of my time origin here, because I'm asking the difference between now and the next time. Let's compute this average waiting time. So when I or Joe arrives, let's apply the inversion formula we just saw a minute ago. So expectation of x of t is equal to lambda Palm expectation of the integral of the waiting time between t0 and t1, given that t0 is exactly an arrival time. So what is that? Well, when I am in between, this is t0, this is t1, for example, what's the waiting time? When a time s is between t0 and t1, the waiting time is t1 minus s. Right. So I have to compute the integral from 0 to t1, or from t0 to t1, of t1 minus s ds. Here there's no probability, there's no Palm calculus, it's just an elementary integral computation. I integrate with respect to s. Capital T1 here is constant. It will not be constant when I will take the expectation, but now I'm just computing the integral here. So this is a linear term. The primitive of that gives a quadratic term. primitive of this is quadratic. If I integrate from t0 to t1, or from 0 to t1, I obtain 1/2 t1 minus s square, which gives 1/2 of t1 minus t0 square. That's the value of this integral. So if I plug the integral here, I obtain that the expectation of xt is lambda over 2 expectation of t0 minus t1 square. The Palm expectation of t0 minus t1 square. What is this Palm expectation? Well, Palm means sample at an arbitrary bus arrival. So it is the average of the square of the interval between buses, between an arbitrary bus arrival and the next one here. So in a simulation, we would estimate it as 1 over n sum of tn plus 1 minus tn square here. So we see that the average waiting time is in fact equal to lambda over 2. Lambda is the number of buses per hour, 3 in the previous quiz, right? But to obtain the average waiting time, we need to have the average of the square of the bus arrival time, of the bus inter-arrival time here. Now, if I introduce what is typically done, the variance, if I call V the variance of the interval between bus arrivals, it's the one that's measured by the bus company. They know all the time t, tn, they do some statistics, and the expectation that they obtain are the Palm expectations. And the variance is the expectation of the square minus the mean square. And by the intensity formula, the mean is 1 over lambda. So if I plug all of this together, I obtain that the expectation of xt is 1/2 1 over lambda plus lambda over 2 times the variance here. Right, so elementary manipulations of the formula here. So we see that the expected time for you or for Joe waiting for the bus is equal to 1 over lambda, that's the intensity divided by 2. That's the formula we would be tempted to derive. If we say there are 3 buses per hour, we can say there's a bus every 20 minutes. So in average, you wait 10 minutes. Right. That's the formula that's the first part here. This average, the 10 minute is here. But that's not the correct answer. The correct answer is this plus lambda over 2 times the variance. So if the variance is 0, if there is exactly a bus every 20 minutes, the answer is yes, you wait in average 10 minutes. If the variance is larger, then you will wait by this plus lambda over 2 times the variance. So that's the price of variability. This explains why there's a difference in viewpoint between the inspector and the customer. If V is very large, then you might wait a long time. And you wait a long time because in general, you're more likely to fall in long intervals of time. Right? So this is one of the classical formulas. We can apply the same to the gatekeeper example we saw before in the example of a multi-core or multiprocessor system that had a gatekeeper that decides which job gets dispatched to which processor. And then we can say here, we can call xt the execution time for a job that arrives at an arbitrary point in time. The execution of a job that arrives at time t. The expectation of xt is for a job that would arrive at an arbitrary point in time versus the Palm expectation of x0, which would be, if I consider special events, the events not of job arrival, but the events at which a processor is made available for the job, which are the red or the green bars here. So we will have a similar thing, and we will see here that we will obtain a similar formula as for the bus case here. One viewpoint gives the other one plus lambda times c, where c is the covariance between the job execution time and the duration of the interval that this job is in here, which was the formula we observed and we derived by more elementary means here. Here I will conclude on this first part by looking at this more general formula here, which is a generalization of what we seen a minute ago. A minute ago, I computed what's the expected waiting time. And I mentioned already that we can do that. If we are able to do that for any arbitrary function of the simulation, we have the full distributions. Here is an illustration of this. If I call x of t in general for any system that has transitions, Tn, and I call x of t the residual time, for time you have to wait for the next event. Again, I stress this is not necessarily a queuing system or a bus system. It's any kind of event, of system that is stationary here. So x of t is the time for the next event, for example, the time until I reach the next waypoint here. Y of t is the same if we look back in the past, is the time elapsed since the last event. And z of t is the same, the sum of the two is the duration of the current interval. Of course, I don't know x of t at time t. If I'm doing the simulation at time t, I don't know x of t. I will know it a bit later. And same thing for z of t. Y of t, I know at time t here. Then by applying exactly the same kind of formulas we've done for the mean, if I do that for an arbitrary test function of x, I will obtain those formulas here. The PDF of x is given by this formula, is lambda, the Palm probability that T1 is larger than S, which is the Palm way of writing things. The more usual way would be this one. It is lambda, the integral from S to plus infinity of the PDF of that interval between two events here. Here, I'm not assuming the events are ID or exponential or independent or anything, but stationary. So the distribution of Tn minus 1 of this interval is the same as that one here, and it has a PDF which is given by this. So if we apply this, we obtain this formula. Interestingly, x and y have the same distribution. So the distribution of the time to the next event is the same as the distribution of the time from the next event for any system of this kind. Right? For it's a law of physics, if you want. If we reverse time, statistically, there's no way to observe the reversal here, which is not a law of physics. Physics says exactly the opposite. The only thing that cannot be reversed is time, which means that stationary systems are not physically realizable, but that's a different philosophical question. The PDF of the time z, which is the sum of the two, x plus y, is obtained by this. That should sound familiar. The probability that the current interval is of duration s, or I say the probability, it's inside the probability density, is proportional to s. It's the probability that an interval is of duration s, but multiplied by s. In fact, that's a formula we have seen when we have talked about the phi length distribution. Here, instead of intervals, we had phi length distribution. Is the same thing here. The probability that I fall in an interval of duration s is proportional to s here. It's not the probability that the interval is s, which would be given by this. Since we multiply by s, we must multiply by a normalizing constant, which is just the intensity here. So those are what can be obtained here. The example we saw a minute ago was this one here, the expectation of zt, the expectation of if we ask what is the average time between buses, we obtain expectation of zt. Now there may be two different viewpoints. There may be the company viewpoint that says I do the statistics of all the intervals. I obtain expectation, Palm expectation of zt, which is 1 over lambda. But you and me, when we arrive at the bus stop, our expectation is at an arbitrary point in time, and for the formula we saw before, it's 1 over lambda plus lambda, the variance here. And this has a name, it's called Feller's paradox. It says that one viewpoint systematically gives larger values than the other one here. And this is the formula we saw already when we talked of intervals last week here. For a Poisson process, then the distribution of the time until the next point arrives, xt, is exponential, right? I write as expected. Why is it expected? For a Poisson process, what is exponential is the time, the duration between two. It's the distribution of the time between two events. But why is it also the distribution of the time until the next event? That's the memoryless property, which is it's a non-aging distribution. So given that you have not yet seen a point, doesn't give you any information on when the next point will occur. So the distribution of the residual time is the same as the distribution of the time of an arbitrary interval seen by arbitrary intervals. The distribution of the elapsed time is the same from what we saw because of this reversibility property. But the distribution of the arbiter of the interval in which we happen to be now, this one is not the same because it can be seen that we can apply the formula before, but we can also see it. In fact, those two is the convolution of those two, which means x and y are independent, in fact. And in average, we are an interval of duration 2 over lambda, even for a Poisson process. That's a very simple and very important example to remember, to really understand what the importance of viewpoint means. A Poisson process means the intervals are completely random, and the time it will take until I see the next event, I have no idea. I know only in average, but given the past, it gives me no information on how much time I will need to wait for it. So the only thing I can say is exponentially distributed with parameter lambda. In particular, the average time between events is 1 over lambda. But now, if I ask somebody specifically, what is the average time of the average interval of which you are now, then the answer will be 2 over lambda. Will not be 1 over lambda, even for Poisson. Again, because now I'm doing a different sampling, I'm asking people, tell me what is your interval. And even if the distribution is memoryless, I'm more likely to find longer intervals. So this is also called Feller's paradox. So even for the Poisson process, there's a factor 2 here. Right? So if you remember that, that should give you a very clear anchor on what is true and what is not true in terms of viewpoints. Voilà, I think it's time to do a little break. After the break, we will see application to simulation.